So let's look at an example of converting Cartesian form to polar form. Here we have z being negative 5 plus 7I, and I want to convert to the r cis theta form. Well, I'll use my relationships here. R squared is going to be a squared plus b squared, where a is negative 5 and b is 7. So r squared is going to be negative 5 squared plus 7 squared, which turns out to be 25 plus 49, or 74. So r equals the square root of 74. R is always going to be a positive value for these purposes. Now, theta is going to be the arctangent of b over a. So theta will be arctan of 7 over negative 5. If we pull out our calculators, we'll take the inverse tangent. Make sure you're in degrees. Of 7 over negative 5. So 7 divided by negative 5. And I get negative 54.462 degrees. Now if I go back to my question, I'm going to plot this imaginary number, or this complex number, on the imaginary or complex plane. And if I go out negative 5 horizontally and down or up 7, then my complex number would be somewhere over here. But my calculator told me that my angle theta was negative 54 degrees. But negative 54 degrees puts me somewhere down here. So I need to apply my arctangent concept and add 180 degrees to get the actual theta in this case. So I go back to my calculator and I add 180, and I get 125.538 degrees. So 125.538 degrees. So now I have my theta and I have my r. So my z value is going to be r cis theta, or root 74 cis 125.538 degrees. And there we go. Now let's look at an example going in the other direction. Given polar format of our complex number, how do we get to Cartesian form? Well, it's just as easy as it was to go in the other direction. So here we just identify r and theta. So r is going to be 3, and theta is our 83 degrees. And then we look at our relationships, and we find that a is r cosine theta. So that's going to be 3 times the cosine of 83 degrees. B is going to be r sine theta. So that's 3 times the sine of 83 degrees. And if we plug that into our calculator, we should find that A will be 0.365 and B will be 2.978. So our complex number in Cartesian form is 0.365 plus 2.978I. All right, so converting from one to the other is a fairly simple process. Let's see what happens when we multiply two complex numbers. So if we're given one complex number to be 3 cis 83 degrees and the second to be 2 cis 41 degrees, what I'm going to do is I'm going to rewrite those as Cartesian representations. That 3 cis 83 is also 3 times the cosine of 83 plus I sine of 83. And the 2 cis 41 is 2 cosine 41 plus I sine 41. Now what I'm going to do is I'm going to work out this multiplication. Just follow along and let's see where we end up. Okay? So the first thing we do is I write this multiplication problem out. Now, to perform this multiplication, I need to FOIL because I have that plus sign in each term. Here we go. Whew. Aren't you lucky I did that for you? So, the 3 and the 2 come out to the front, and then I get cosine 83, cosine 41, the first, times I sine 83, cosine 41. So that's the inner values there, plus the I cosine 83 sine 41, and that's the outer 2. And finally, when I multiply the last, I get I squared sine 83 sine 41. But let's remember that I squared is actually negative 1. So what that turns out to be is I get the cosine of 83 times cosine of 41 minus the sine of 83 sine 41 plus the two I terms added together. Sine 83 cosine 41 plus cosine 83 sine 41. All right, this looks kind of messy, but now what we're going to do is go back to our trigonometric identities. Ha, you thought you were through with those, didn't you? Here, this first pair of terms, I have a cosine cosine minus a sine sine. And if we remember our cosine or our trigonometric identities for this type of combination, we remember that that's the cosine of A plus B. And here on the other side with the I term, I have sine cosine plus cosine sine. And that trigonometric identity is the sine of A plus B. So that allows me to rewrite these as the cosine of 83 plus 41, since A was 83 and B was 41, and plus I times the sine of 83 plus 41, or since, again, A was 83 and B was 41. If I simplify those two terms, I get cosine of 124 and the sine of 124, or condensed into our 6 cis 124 degrees. Now let's look at how our answer compares to our question. Do I need to go through all these steps every time I multiply two complex numbers in polar form? Well, where did this 6 come from? Well, it came from the 3 times the 2. And where did this 124 degrees come from? Well, it came from adding the 83 and the 41. So anytime I multiply two complex numbers in polar form, I can get to the answer just by multiplying the r values and adding the theta values. So we have that pattern. Turns out we have patterns for division and for finding the reciprocal as well. For division, the same thing happens, except now I divide my first r value by the second, and I subtract my second theta value from the first. The reciprocal also has an easy formula. Our answer, if we want to take the reciprocal of a complex number, is simply 1 over the modulus cis of the negative original angle. Let's try a few problems here. If I want to find the reciprocal, let's look at our formulas again, of 2 cis 29 degrees. Well, 1 over z is just going to be 1 over the modulus, so 1 over 2, cis of the negative angle, so negative 29 degrees. Not that hard. There we go. Let's see if we can extend these ideas. First, let's look at our formulas here. If I want to find z to the 5th power of 2 cis 29, well, I can think of that as an extended multiplication problem. So z to the 5th would be 2 cis 29 times 2 cis 29 times 2 cis 29 times 2 cis 29 times 2 cis 29. If I work out a pair of these separately, for instance this first pair, well, I just remember that I multiply the first r times the second r and add the two angles. So this piece becomes 4 cis 29 plus 29. If I multiply that by another 2 cis 29, it becomes 8 cis, and now I'll have 29 plus 29 plus 29, or 3 29s. And if I do that 2 more times, I'll multiply 8 by another pair of 2s, so I'll end up with 32 cis, and I'll add 5 29s before I'm done. So 5 times 29 is 145. So my answer should be 32 cis 145. This process would work for any power I choose to raise z to. So we can come up with a formula for finding a complex number raised to a power. So what would that formula be? If I was going to raise z to any power, what should that formula be? I'll show it on the next slide, but see if you can figure it out. Here we go. Yes. So if I'm raising z to some power, then I take the original length, raise that to a power, and I take the original angle and multiply by that exponent. We call this property, or de Moivre's theorem. He was the first to discover it and prove it. Now, the neat thing about this theorem is that it not only works for integer exponents, it also works for fractional exponents like 1/2. So I can actually find roots of complex numbers using this property. Let's see how that works. If I want to find the cube roots of z when z is 8 cis 60 degrees, well, I will identify my exponent here. I can rewrite this cube root of z as z to the 1/3. So that means that my n value is 1/3 when my z to the n formula was r to the n cis n theta. So there is one wrinkle to this problem that we need to keep in mind. Here, this 8 cis 60 degrees, just like when we were discussing polar coordinates originally, can be expressed with coterminal angles. So 8 cis 60 could also be 8 cis 420, because I could add 360 degrees, or 8 cis 780, or 8 cis 60 plus multiples of 360 degrees. And we're going to use that fact to help us find all the cube roots of z. So let's start with that expression, 8 cis 60 plus 360n, and I'm going to apply de Moivre's theorem. So if that's z, then z to the 1/3 is going to be 8 to the 1/3 cis 1/3 times the quantity 6 plus 360n. Now, I'm going to simplify here. Z to the 1/3 is going to be equal to 2, that's the cube root of 8, cis 20, 1/3 is 60, plus 120n. So let's see if we can find specific solutions now that we have this expression for z to the 1/3. If I let n be 0, then my first cube root of z is 2 cis 20. If I let n be 1, I find that coterminal angle, then z to the 1/3 will be 2 cis 20 plus 120, or 140. And if I add another 120, so n equals 2, then I get 2 cis 260. If I add another value of n, I end up with 2 cis 380. But if you'll notice, 380 degrees and 20 degrees are coterminal. They're actually both in the first quadrant. And I'll get continuous coterminal angles after this if I keep adding n values. But these three original values, 20, 140, and 260, are unique. If I were going to plot those three values on the complex plane, they would look something like this. Here's my first. 2 units out at 20 degrees. My second answer was 2 units out at 140 degrees. So that's this one right here. And finally, my third was 2 units away at 260 degrees. And remember, the next one I found was 380 degrees, which just brings me back to the 20 degree solution. So I have 3 unique solutions for cube roots. 2 cis 20, 2 cis 140, or 2 cis 260. Remember that when you take roots of your complex numbers, you're going to have more than one solution.